what exactly are these data structures? Dude, like I'm a bachelor student. मैंने ये कभी लाइफ में पहली बार सुन रहा हूँ. कभी क्या, चल मैं लाइफ में पहली बार सुन रहा हूँ. मुझे रेड ब्लैक ट्रीज पता नहीं है, एवियल ट्रीज क्या है पता नहीं है. Like what exactly are those? Tell me that first. Okay, more advanced concepts and how we can resolve all of the limitations of the LSM trees in the next thing. And after that, B trees and R trees, we will be done with the database evolution part, and then we will start the new concept about the data engineering. Instead of storing every single entry in the hash indexes, we would store a range of queries, right? A range of the keys. How databases works, how databases return the queries. When you fire up select star from this table, and then it will return all of the things in blazingly fast, in like literally milliseconds of the time, and how it actually works. Hello everyone, welcome back to this channel. If you're new here, my name is Amey and I teach data engineering concepts in really simplified terms. And if you're watching this episode directly, this is the part 2 of the series Understanding Databases, how it evolved from one form to the whatever current we have. So we are at the stage of hash indexes. If you have not watched the part 1 of this series, go check out the part 1. You would need that. This is the prerequisite for this part. So without a further ado, let's get started with this episode. Okay, so in the last video, we saw, or we learned about the compaction, what compaction means, how the merging of the two compactions, or the two segments works in the database, and how does it go. We went over all of the details over it. I'm looking at this screen because like I can see my myself and the iPad screen over here. So don't mind. I'll look at this screen as well. I'll look at the camera. I'll be looking at the camera directly, but I need to make sure whatever I'm saying, whatever I'm presenting, it's right there and it's visible or not. Okay. So we went over compaction and we were at the hash indexes. We were understanding the databases at the hash indexes. So just to give a brief recap, what hash indexes would do is we will use our initial thought process of appending it to the file. Whenever data comes, whenever we are creating a new transaction or new entry, we will append it to the file directly, and then we will store its hash indexes. Whenever a new transaction is appended, we will store the key and the value to be as the whatever the memory address that the new file starts in. So whenever we want to search or whenever we want to get something out of the database, हम लोग क्या करेंगे कि we will just go there, see the latest file offset, and then we will go on that file offset. We will extract that JSON file, CSV file, whatever the format the file has been written in. We'll extract that and we will extract the key to be searched in, and we will return out the values. Okay, that's what we saw so far. But what are some of the challenges or the considerations or the pros of this method, right? So first of all, file format. Okay, so we are using CSV file format or JSON, right? So these file formats can be simple, but it would be more simple and it would be more useful for us to use byte file format. So in this byte file formats, what it will do, what our database will do is it will store our strings at bytecode and then will process it. It would simplify the overall appending strategy, appending it to the last last sentence of the file. It would simplify that strategy. So maybe using byte file format will help us, but JSON and CSV would do good. The second challenge is the deletion of records. So how can we handle the deletion of the records? That's the main reason, right? That's the main thing, right? So okay, so what could be our deletion strategy? हम लोग database को कैसे बताएं कि ये particular record delete हुआ है and we don't want to take any updates. So let's say we deleted the entry B. Okay, and so how should we update this thing, merging strategy, to ignore all of the B values? How will we update it? Okay, so we need to add one more logic to this deletion logic, which we will call as a special file. Okay, and okay, a special file which would only contain the deleted keys, right? And we would tell database, and we will ask database, so hey database, whenever you encounter any keys from this deleted file, you should ignore all of the updates from the segment files that we have. So these are our segment files, right? This is segment file 1, this is segment file 2, and then the compaction happens between the two, and then we get the new segment file, right? We saw in the last video, whenever this gets full, we will discard all of the previous updates. So let's say we have a new input over here. Let's say a delete file input. Okay, delete file input, and it contains the entry B. Okay, so while merging it, it will check if the latest key B is present in the deleted file or not. If it is present, then it will discard this value it will discard this value. Okay, so whatever this deleted file was, that is known as tombstones. Like this process, uh, so like whenever we are appending a special deletion record to a data file, that is a tombstone basically. Okay, that is known as tombstones. And this deletion and merging and removing the tombstones as well is a critical part as a data engineer that you must know. Because let's say you're working with Cassandra, and there are problems where you have to deal with the tombstones. So what problems does it occur in Cassandra is generally your tombstones files get a lot bigger. So let's say you have very frequent deletes, so your tombstones file gets bigger, and referring to that file every time will cost O of n, because you have to check for the keys in tombstone files, and then you have to also refer to the new segmented file every time. Though your compaction and merging strategies only work on segmented files, but your tombstone file gets bigger and bigger and bigger every time, but every time you have to refer it to this bigger file, right? So that is one of the common errors or common problems that you need to solve in tombstones. Generally, database takes care of it. The modern databases takes care of merging and pruning the tombstone files on its own in the backend thread, but sometimes you have to manually manage it. Okay, so that is about deletion of the records. What about crash recovery? Your database can crash at any time. So what is the mechanism that you should make, right? So currently अपना system क्या है? अब मैं just हिंदी में switch करता हूँ because I told you in the last video. Sometimes क्या होता है कि you are storing hash indexes where? In RAM, correct? You're storing it in RAM, right? To access it faster. But whenever your database crashes or that computer restarts, we all know whenever a computer restarts, your memory is flushed out, and it will just restart from scratch again. So all of the indexes that you have stored into the RAM are lost now. or last now. Okay, so what you can do in here is you can create these indexes again by referring it to the segment files, because originally you created those hash indexes using the segment file itself. But if the segment files are stored on the disk, and they can be large, right, they can be humongous in nature if they're not pruned, or if they're not merged or compacted using the strategy. And that can take a lot of time to load the hash indexes in memory again from the segment files. And that is the problem that we should look out for. Okay, so how to solve this problem? Many databases, what they do is they will from time to time they will take the snapshot of the segment file and create a hash index out of it, and will store that hash index snapshot in memory, in into the disk. And whenever this crash happens, they will just, rather than rather than forming the hash indexes again from the segment file, वो लोग क्या करेंगे कि सीधा हैश इंडेक्स का स्नैपशॉट ही उठा लेंगे. जो भी लेटेस्ट हैश इंडेक्स है उसका स्नैपशॉट उठा लो, मेमोरी में डाल दो. दैट्स इट. That's the solution to this, and that's the easier one. Okay, straightforward one. Now coming to the next part, what happens to the partially written record? So your database can crash at any time. We looked at what will happen if our database crashes, but let's say it is writing some record, and while writing the record itself the database crashed. What should we do with that? So we can include some checksum mechanism to identify these corrupt records and just ignore them. Or we can have a flag or an offset as well, like till this offset we have processed all of the records, but after that we have not processed. And then whenever we encountered any ignored records, we can just start processing from the offset record, and then do it again. That's the only thing we can do it over here. Okay, concurrency control. So what do I mean by concurrency control is how faster, or how much parallelism that I can involve in writing and reading of this database. Currently we are looking at the hash index mechanism or hash index phase of the evolution. So consider it as like we saw the Stone Age, which is just appending the file and just reading it in, or writing it in O of 1 but reading it in O of n. Then we came to know like we can store the hash indexes. So hash indexes store करना मतलब क्या कि every time there is a new transaction appended to the file, we will just store the new transactions hash or new transactions memory location into the RAM, so that whenever there's a get request, we will just know कि RAM में कहाँ पे RAM से हम लोग hash index से लेंगे कि वो नया फाइल किधर है, उधर जाके ही हम लोग बस रेफर करेंगे. That's it, straightforward. So we sacrificed our memory to win at the speed. That's the solution. Okay, but how fast we can read it or how fast we can write it, that's the concurrency control. Okay, so with our current mechanism, the files should be immutable, right? At least while writing, because if it's mutable, then many threads we can open up, and this thread, when writing it onto the file, can incur the lock onto the file, so that these threads cannot write while the first thread is writing onto the file, right? Because it can happen that multiple threads are trying to write to the file at the same time, and they want to modify or they want to write the same record onto the file, and it is not allowed. So concurrency control for writing, for now it's single threaded, but for reading it can be multi-threaded, right? We can read using multiple threads in parallel. So concurrency control for now is single thread for writing and multiple thread for reading. Why we have made these choices is for our current hash index based and append only system. This is the only thing that we can do. Okay, that's it. So if the hash index is so good, why do the newer database systems even exist, right? So there are some limitations to the hash index systems as well. And what are those limitations is, first limitations is RAM. RAM is the choke point. RAM is the choke point because we have only the limited RAM in one single computer, right? But we can have technically unlimited storage system. So the first limitation is the RAM sizes. So if the database size increases, the hash indexes can increase in size. And it can surpass the RAM's size as well. It can surpass the RAM's size as well. Okay. So you might say, Amey, if we have the unlimited storage, why can't just we write the data into the disk, that hash indexes into the disk from time to time? And that's a really good thought process, and that's the more intuitive thought process, and that's the most obvious thought process, right? But the thing with writing on the disk is it involves disk IO and overhead from reading it from the disk and writing it to the disk, which is slower. The disk IO is slower. Okay. So everyone talks about disk IO, but what exactly is disk IO? I'm a newbie. Tell me about this disk IO. So disk IO is nothing but disk input and disk output, which is writing to the disk and reading out of the disk. That is disk IO. That's it. Simple as that. So why writing and reading from the disk is slower? So that you need to learn from the computer architecture class, because RAM is closer to the CPU and all. It has separate buses to read it from the RAM because RAM size is also lower. So it will be faster. The disk is, you can go and just read about why disk IO is slower and why reading and writing to the RAM is faster. That's your homework. Okay, and comment down in the description if you know it already, and help others to understand it. Okay, and help me also understand it. I also don't know. Just kidding, I know. But help everyone understand it. Okay, that's the one thing. Okay, the second limitation is, okay, the second limitation is range queries. Range queries. So since we are just storing the latest documents, memory address, we cannot perform the things such as, okay, give me the data from this date to that date, or this particular key to that particular key, right? So let's say I want data from 000 to 999. That is not possible, or it's difficult rather. To know this, we need to scan all of the entries, often again. So, and what's the point of storing the hash indexes then if we have to search it in often, right? It's pretty obvious. So the range queries are difficult. But how to solve these problems then? How to solve these problems? So you might say, Amey, what we can do is we can just sort all of the keys, right? So it is going to take O of n time. But what if we sort all of the keys over here and then use the binary search to search it in log n time, right? That would be perfect, right? So just to get you the context, what even I'm talking about, right? Where are we searching it? What are we searching it? So we are talking about hash indexes in the RAM. Hash indexes in the RAM. And segment files in storage. Segment files in the storage. Okay. So how do we solve it? How do we solve these problems? So there is something called as sorted string tables. I know you might not know it. Obviously you don't know it, that's why you're here. So what are sorted string tables, right? So instead, so what is our current system? So our current system is we are using log files. And by log here, the word log means the logbook wala log. Okay. So whenever someone comes into our apartment, watchman logs their entry. So it's that log file. Okay. Not logarithmic scale or something like that. Okay. These are the log files. We are just writing the transaction log. Whenever there's a transaction into the database, we are just appending it to the file system. And which is O of 1, but searching is still O of n somewhat, right? Even if it's hash map, we are getting it to the file, but through the file we are going off n, right? But and we have this range query problem here with us. So to solve it, why can't we just sort? Why can't we just sort all of the keys in the file? All of the keys in the file, right? But Amey, isn't it costly? Isn't sorting its n log n operation? Isn't it costly? हम तो O of 1 में कर रहे हैं. n log n तो बोल रहा है sort करने का. But we'll get into that shortly. Or let me just tell you, there are data structures, much sophisticated data structures, which are red black trees and AVL trees. Okay, so what exactly are these data structures? Dude, like I'm a bachelor student. मैंने ये कभी लाइफ में पहली बार सुन रहा हूँ. कभी क्या, चल मैं लाइफ में पहली बार सुन रहा हूँ. मुझे रेड ब्लैक ट्रीज पता नहीं है, एवियल ट्रीज क्या है पता नहीं है. Like what exactly are those? Tell me that first. Okay, so don't worry, I've been always telling you guys that I've been there, done that, right? तो मुझे भी नहीं पता था. Simple as that. मुझे भी नहीं पता था. But there is a guy who is Kunal Kushwaha. Really good guy. Just refer his video. He has made detailed videos about this. And comment down in the comment section as well if you want to learn more about these concepts from me, and I will make that video. But for now, refer to the Kunal Kushwaha's video, and I will just go over the overview of these two trees. Okay, so for the lookups, right, for the finding any value, both of these trees get used. AVL trees are much more faster than the red black trees, but the key advantage of both of these trees are these are self-balancing trees. Okay, so these two trees are self-balancing trees. What are self-balancing trees and everything you will get to know from Kunal Kushwaha's video. But the basic operation is whenever the tree is modified, this tree will self-balance in such a way that it will maintain the order. It will maintain the order of the tree in log of n time. and that's the biggest advantage. So instead of n login, it would take log n time, and that's the main advantage of it. You can go over this in the details with the Kunal Kushwaha video, but I will just move forward with the with our topic of this thing. So let's say we have this mechanism to sort all of the keys in the file, right? So whenever a new key is inserted, our data is stored in AVL tree or the RAID tree format, and then the tree will balance out itself in such a way that it will maintain the overall order and the overall structure of the tree. Okay, maybe this is lower, this is root, and this is right, left, root, and right. And then whenever left, root, and right, and whenever a new key is inserted, it will balance in such a way that it will maintain this order. Okay, that's the thing. So what sorting give us? Why to sort? Okay, so sorting gives us the main advantage is lookups. Lookups happen in log n time, binary search log n time, and that is the main advantage of it. So let's take an example and see how this works, right? So this is the screenshot that I took from the book Designing Data Intensive Application, and whatever I'm talking about, this is covered, everything is covered in that book. If you're finding hard to learn from me from this video, you can refer it to that book. But if you like me explaining these concepts, just continue watching it. Okay, so let's say this is our first segment, right? This is our second segment file, and this is our third segment file. And if you see, handbag, handful, handicap, handkerchief, handlebars, and hand printed, everything is sorted in order, right? So how merging process works is, we know the segment 3 would be the latest segment, right? So compaction and merging process, if you are into lead code, you must have solved the question which is merging the sorted array, and it is exactly like the merge sort, and it is exactly that algorithm. So what we will do is, we will have pointers here, we'll have pointer here, here, and here. Okay, and we will check which one of these is lesser, or the like comes first, lexicographically or alphabetically, right? So we know that handbag is the first thing. Okay, but does handbag appear here, 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 here? So we would assume the handbag's latest entry is this one, and we would have it stored it over here. Okay, then the pointer for this particular segment shifts from here to here. Okay, so we are at handful, we are at handcuffs, and we are at handful. Okay, out of these three, the handcuffs is lexicographically smallest, so we will have the second entry in our compaction process, this. Okay, then we would be handful here, handful here, and handful here. Okay, but the latest entry is from the segment 3. We all know segment 1 and segment 2 are already full. That's why we created segment 3 in the first place. So what our compaction will tell is, discard these values from the previous one and have this value from the handful over here, right? And the algorithm continues with all of these three files, and we will have the new compacted and merged file available over here. Okay, so since this is sorted in order, and these are the string values, we would call it as sorted string table, or short form it as SST. Simple as that, straightforward, right? So our compaction and merging process looks like this. It is like a merge sort, and it will happen in log n time. Okay, okay, so before that we covered, if the key is in multiple files, where do we refer? This file. Okay, that is what I wanted to highlight. But how it will solve the range query problems, right? That is the question. That is the main disadvantage of the hash index as well. That's why we are using this particular thing in the first place, right? So what we can do is, instead of storing all of the indexes, let's say handbag का new entry आ गया, हमने index में डाल दिया, हैंडफुल का आ गया, हमने इंडेक्स में डाल दिया, हैंडीकैप का आ गया, हमने इंडेक्स में डाल दिया, हैंकरचिफ का आ गया, इंडेक्स में डाल दिया. बट व्हाट्स द पॉइंट ऑफ दिस, राइट? वी हैव सॉर्टेड इट. तो हम लोग सॉर्टिंग का कुछ एडवांटेज उठा सकते हैं क्या? उठा सकते हैं. And what that would be is, instead of storing every single entry in the hash indexes, we would store a range of queries, right? A range of the keys. So let's say we are storing handbags key. Then maybe we might skip a few entries and we will store handlebar entry. Okay. But since these are sorted, whenever search term comes for the handicap, we would know it resides between handbag and handlebars for sure. And we have hash indexes for both of these. So we will just perform binary search over here. And we would find handicap in log of n time. How log of n time? How binary search works? You can search over internet and you will find it. Okay. So what this will do is, this will reduce our RAM occupancy of hash indexes, from storing everything to storing some of the entries. So let's take an example and let's understand with a simple example. Again, this screenshot is taken from the book Designing Data Intensive Applications. Okay. So let's say we are searching for the word handiwork over here. Okay. And this is our sparse index in memory, which stores the key and the byte offset. Okay. So why byte offset? I told you in the first place, right? In here, file format. So instead of CSV, if we use the byte files, we will have the byte offset already with us. Okay. So that is the byte. Okay, so that is the byte offset, like where it starts in the memory from. So let's say handbag, hand. So let's say the hand prefix starts with 91541 memory, right? On the disk. This is on the disk. This is in RAM. So this thing is in RAM. This thing is in disk. So using the RAM's values, we are not searching in O of n, like we are not searching all of the values in the disk, but we are reducing our search space. We are reducing our search space. How we are reducing our search space is, so let's say we are looking at the handiwork, right? So we have hamrock, we have handbag, we have handsome, and we have hangouts. Okay. So we know that hammock is does start at 100491, and handbag starts at 10212134. And we know handiwork resides between the it like it will come after this point, but it will definitely be before this, right? It will definitely be before this and it will definitely be after this. Okay. So what we are saying is, go to the disk to this offset, which will point to you with this memory address, and then take it as left, consider it as right, and then find the middle equal to handiwork in log of n time. And here n is the size of this block. R minus L is the size is n, not the entire n. So we are reducing the space and we are searching it in binary search. It is efficient, right? It is super duper fast. So previously what we were doing is, we were searching it in O of n time when we are appending it to the log file. But that costs a lot. Let's say there are billions and trillions of rows, it will scan all of the rows. But what we are doing is, instead of trillion rows, we are just saying you here are 1,000 rows and use binary search on 1,000 rows, right? So if you know the math, 2 power 10 is 1024. So even if there are 1,000 rows, for our algorithm it will take only 10 steps, only 10 steps. And just to remind you, a computer can perform 9 to the power 10 to the power 9 cycles in 1 second, राइट? सो जो जो हम लोग बोलते हैं कि मेरा प्रोसेसर 9 गीगा का है, 10 GHz का है. व्हाट इज दिस गीगाहर्ट्ज? इट इज 10 to the power 9, राइट? हर्ट्ज मीन्स व्हाट? पर सेकेंड, per second. Giga means what? 10 to the power 9, right? So it performs 10 to the power 9 operations per second. And here we only have 1,000 operations. 1,000 operations to go over in logarithmic time, which is almost 10 operations. So do you understand how fast this is? Like milliseconds responses में तुम लोगों को out of trillions of databases, out of trillions of entries, you are getting the results in very 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 less time. And that's how the database works. Isn't it fascinating? I mean, I literally have goosebumps. Okay, let me show you this. I literally have goosebumps right now. I don't know if you can see it or not, but मुझे तो बहुत थ्रिल महसूस हो रहा है ये सब, ये सब अंडरस्टैंड करके भी कि वाओ, डेटाबेसेस आर सो फास्ट एंड इट हैज़ इवॉल्व्ड ओवर टाइम. मतलब पहले लॉग एंड था, फिर प्रॉब्लम आया उसको सॉल्व किया, प्रॉब्लम आया उसको सॉल्व किया, प्रॉब्लम आया उसको ऑप्टिमाइज किया, एंड दैट्स हाउ इट वर्क, राइट? सो हमने सॉर्ट किया, हमने मेमोरी बचाई. पहले हम लोगों ने हैश इंडेक्स बनाया ताकि हम लोग फास्ट सर्च कर पाए इन लाइक instead of looking at entire file, we would just only look at that file. बट हम लोग उस पर रेंज क्वेरीज नहीं परफॉर्म कर सकते थे, इसलिए हम लोगों ने सॉर्ट किया. फिर सॉर्ट करने से हम लोगों को ये एडवांटेज मिला कि हम लोग स्पेसिफिक रेंज में बाइनरी सर्च में हम लोग सर्च कर सकते हैं, विच इज़ मोर फास्टर, विच इज़ मोर ऑप्टिमाइज्ड. तो हम लोग ये डिस्क पे स्टोर्ड कैसे है भाई? हमें ये तो बता भाई कि ये सब स्टोर्ड कैसे है. व्हाट इज द डेटा स्ट्रक्चर? इज इट अ प्लेन फाइल और व्हाट इज इट? व्हाट इज द फॉर्मेट ऑफ दिस? सो मैंने आपको बताया एवीएल ट्रीज है, रेड ब्लैक ट्रीज है, वो डेटा स्ट्रक्चर में हम लोग सेव कर सकते हैं. बट द रीसेंट डेटाबेसेस स्टोर इट एज बी ट्रीज, एंड we will go it in the part 3 of this video, how databases work and how databases evolve. What are B trees? What are R trees? Those two are the recent ones that we go over, right? But let me tell you one more important topic or one more important thing about this is this sparse index in memory, right? Whatever we store. Okay, let me recap it one more time. So before that, as I was telling, right, B trees and R trees, so these are used on disk. Okay, I made a mistake over there. AVL trees and AVL trees and the red black trees are used for the storing hash indexes in memory, but these things will be stored as B trees in storage. Like we can maintain the sorted order in memory using, okay, discard, fuck it, I'll just cut it over here. Okay, just let me just recap how does our database is working now. Okay, after evolving one more stage, Pikachu to Raichu. हम लोग अभी राइचू में आ गए. व्हाट एम आई सेइंग? हम लोग अभी इवॉल्व डेटाबेस में आ गए हैं. तो हमारा डेटाबेस क्या करता है कि whenever a write request comes, okay, it will be updated in RAM first, it will be outdated in the RAM data structure first, which is AVL trees. Okay, and since we are storing this in memory, it is often known as memtables, right? And we can store it as AVL trees or red black trees. Okay, so we are storing it in still in memory, right? We are storing that in still memory. But what happens if now this index goes about some threshold, right? So if memtable is greater than some threshold that we should define as a user or as a database creator, once it is greater than that threshold, we would flush this memory onto the disk, on the disk, right? And while this is happening, we can create a new memtable instance in RAM, and we can serve new write requests there. ओके, सो assume करो अपने पास ए मेम टेबल है और बी मेम टेबल, ठीक है? ए फुल हो गया, ए हम लोग मेमोरी में डाल दिए। ये जब तक जा रहा है तब तक एक और राइट रिक्वेस्ट आ गई, तो वी विल क्रिएट ए न्यू इंस्टेड ऑफ बी, ए न्यू इंस्टेंस, and then we will write all of the requests in the a new table while this is being getting dumped into the memory. Simple, right? So this is how our writes will work, and the sorted structure will be maintained on the disk as it is in the RAM using the B trees, or using the same tree algorithm in the disk as well instead of RAM, as supposed in RAM. Okay, so now comes to the part. Okay, write to sorted है. What about reads? Tell me about reads. Okay, एक read request आ गई, तो मैं डेटा कहाँ से fetch करूँ, कैसे fetch करूँ, कितना fast fetch करूँ? So that thing happens from the first we will check in the RAM, right? RAM, it is faster. Anyway, anyhow, any day, checking in the RAM is faster. Querying from the RAM, getting the data from RAM is faster than it is. So we will check first in the RAM. If the data to be queried is available in the RAM, we will just return it, because we know whatever the data is in the RAM is the latest and the greatest and the most updated one. We will just return it. If it is not present in the RAM, we will check the most recent segment from the memory. So what I mean by that is we have multiple segment files, right? So let's say this was our a mem table, this is dumped in segment 1, then a new आ गया, this is this, then a new आ गया, this is this, but अब तक compaction नहीं हुआ है, तो अपने पास तीन सेगमेंट बन गए हैं डिस्क पे। तो हमको एक रीड रिक्वेस्ट आया जो हमने रैम में देखा, रैम में नहीं है, तो मोस्ट लेटेस्ट एंड ग्रेटेस्ट एंट्री किस में होगा? ऑब्वियसली सेगमेंट 3 में होगा, राइट? क्योंकि हमने अब तक कॉम्पैक्शन ट्रिगर नहीं हुआ है बैक एंड पे, क्योंकि ये फाइल अब तक वो 50 MB रीच नहीं हुआ है जो अपने थ्रेशोल्ड सेट किया था, याद है? रेफर टू द पार्ट 1 फॉर दैट वीडियो। ओके, तो हम लोग क्या करेंगे, फर्स्ट इसमें चेक करेंगे कि अगर वो की इसमें है तो इससे रिटर्न करेंगे, इसमें नहीं है तो इसमें जाएंगे, इसमें नहीं है तो इसमें जाएंगे, एंड सो ऑन, जब तक की नहीं मिलता। और अगर नहीं है तो विल रिटर्न कि है ही नहीं की, भाई जो तू सर्च कर रहा है वो डेटाबेस में एग्जिस्ट ही नहीं करता। एंड वाइल इट इज हैपनिंग, बैक एंड पे हमारा कॉम्पैक्शन एंड मर्जिंग प्रोसेस विल बी कीप ऑन रनिंग। ओके, सो फर्स्ट रीड रिक्वेस्ट आएगा, वी विल चेक इट इन द रैम, रैम में नहीं है, जाएगा सेगमेंट टेबल्स में इन क्रोनोलॉजिकली रिवर्स ऑर्डर, जो सबसे लेट हुआ उसमें सबसे ज़्यादा लेटेस्ट एंट्री होगी। अगर इसमें नहीं है तो एरर आउट। ठीक है। इन सब ये सब जब तक होता है तब तक अपना ये एल्गोरिथम चल रहा है, मर्जिंग एंड कॉम्पैक्शन। Merging and compaction, and that's how the databases really works. I mean, फर्स्ट मतलब बड़ा बड़ा मोटा मोटा अभी भी ओवरऑल हाई लेवल यही है। कसांड्रा में भी यही होता है। मैं कसांड्रा कसांड्रा इतना क्यों करता हूँ, क्योंकि मैंने वर्क किया है कसांड्रा पे, मुझे पता है कसांड्रा वर्क्स इन रिंग आर्किटेक्चर, मास्टर स्लेव आर्किटेक्चर, वो सब हम लोग आगे जाके पढ़ेंगे। बट ओवरऑल द हाई लेवल आर्किटेक्चर इज, हाई लेवल आइडिया इज दिस: पहला मेमोरी में जाएगा डेटा, फिर मेमोरी से फ्लश आउट होके डिस्क में जाएगा, डिस्क से रीड एंड राइट रिक्वेस्ट कैसे होता है वो मैंने आपको बता दिया है, राइट रिक्वेस्ट कैसे होता है मैंने बता दिया है, कॉम्पैक्शन एंड मर्जिंग कैसे होता है ये भी मैंने बता दिया है। ओके, तो मैंने आपको बता दिया है कि हाउ रीड्स एंड राइट वर्क्स, हाउ कॉम्पैक्शन वर्क्स, हाउ डज इट लॉग्स एवरीथिंग, हाउ डज इट मर्ज एंड कॉम्पैक्ट, हाउ डज इट स्टोर it in memory and everything. So this concept overall is known as LSM trees. Okay, so LSM trees मतलब क्या है? LSM trees, this is nothing but log. We are storing logs, right? So it is log structure, and we are merging it, right? We are merging it, merge tree. So it is log structured merge tree, that's it. So it was originally was described by Patrick O'Neill under the name log structure merge tree. So this indexing strategy, whatever we are using it, this is named as, or first coined as, by the Patrick O'Neill, and he built their entire his work on log structured file systems from there. So he coined that term. Again, you can find this in the book Designing Data Intensive Applications. So there are indexed databases as well which use this LSM tree concept, which is Elasticsearch and Apache Solar, which are lightning fast to just these databases are used for lookups. And whenever there is a use case where you have to find data faster, you have to just retrieve data faster, these two particular databases are used, Elasticsearch and Apache Solar. So let me give a real life example that I use. So in one of the hackathons we needed to find out, so whenever a user fires up a query, let's say a person wearing a red shirt. So what we needed to do was so what we used to do was we used to convert this query into the embeddings. So what are embeddings and everything? This is a separate video, but let's just understand we need to search that query in the database, from the database, right? And we needed to search it faster. That's where we used Elasticsearch to look up. Okay, but let me know in the comments if you want a detailed video explaining my project for hackathon. I explained that project in my interviews, and it was a very good project, I would say, that I am proud of. But yeah, let me know in the comments if you want a detailed video on that. I'll make it. But what are some of the performance optimizations that we can use? Right. So the obvious one for this LSM and SSD tables is it is highly dependent on I mean one thing, right? Or it assumes that the key is present in the database. That's why it will be faster. We are assuming it. So let's take again this example. So there is handbag, handful, handicap, handiwork, handlers. But let's say I'm searching for zebra. Huh? And I'm searching for zebra, right? And we can see zebra doesn't exist in the database. So first what we'll do is we will go in O of n time in the RAM. We will check zebra exists. No, it doesn't. We will check all of the segment files. It will exist. No, it does not. But that's the key point, right? If the key doesn't exist, it will go and check every single key if that matches or not. So what can be done? So let me just optimize. Let me just write it for your reference. It can degrade the performance if the key doesn't exist. I don't know if the key doesn't exist. Okay. So what can we do to solve this problem? So there is something called as Bloom filters. Wow, fancy term, Amey. What does it mean? So Bloom filters are nothing but a detailed hash. Okay, maybe a detailed hash, because let's say hammock and handbag. So it will have some more words or some more keys from these two. So it would approximate the distance between the two words. What I mean by that is it will detail out. So instead of having, so let's say there are millions of words exist between these two words, right? So we have to scan millions of rows 10 to the power 6 time. But what that Bloom filter will do is instead of 10.6, it will have some more words, filler words in between, which can approximate our search space. So instead of 10 to the power 6, maybe we have 100 entries. Like per 100 entries, we have some more words over here. So whenever a search term like zebra comes, we will search if this exists in the entire database, entire hash map or not. If it doesn't exist in the hash map, we can just return it, bro. There is no need to search in our segment files, because such key doesn't exist in our memory. So it shouldn't exist in the storage tables as well. So that's the overall high level idea about the Bloom filters. I will go in detail in separate video, because this video is already an hour long, and it might be boring for some of you guys. Most of you guys won't even watch till this point. If you are watching till this point, and if you are really finding a lot of value from this, please hit that subscribe button, because I'm not even kidding. It is 3:30. It is 3:38 in the morning right now, and I'm still recording this video for you guys. 3:38 in the morning. So do subscribe to this channel. It means a lot to me. It means a lot to me. Okay? And it will motivate a lot. Also, okay, some more of performance optimization is there are techniques, there are many databases used to optimize merging and compaction time, right? When exactly should the merging and compaction should happen? It shouldn't be like randomly happen, right? It shouldn't happen randomly. So there are size level, and there are size tiered and leveled compactions. So the most common options are size level, size tiered, and the leveled compactions. The rocks DB and the levels DB use level compaction, hence the name levels DB. And the HBase or the Cassandra uses both of it. Okay, so in size tiered compaction, the newer and the smaller SST tables are successively merged into the older and the larger SST tables. But in the leveled compaction, the key ranges is split up into the smaller SST tables, and older data is moved into the separate levels, which allows the compaction to proceed more incrementally and use less disk space. So the compaction happens in two tiers, basically a size tier and a level tier. The databases like levels db and the rocks db uses the level compaction, and the size, the HBase and Cassandra, these type of databases uses the size tiered, or the both. They uses both of the compactions. Okay, so in size tiered compaction, what happens is the newer segment files are merged into the older file. So what I mean by that is, सो नया सेगमेंट फाइल बन गया, मर्ज हो गया, नया सेगमेंट फाइल हो गया, मर्ज हो गया, नया सेगमेंट फाइल हो गया, मर्ज हो गया, एंड दिस merged file will get larger and larger, and then this will act as a new segment file, and once it reaches that 50 MB limit, this will again be added into the compaction queue, and then it will again act as the segment 4, and then the new merged compaction file will be created again, and that's how it will work in this thing. In the level tiered compaction, what will happen is a key ranges are split up into the smaller SST tables. Okay, the key ranges are split up into the smaller SST tables, and the older data is moved into the one one separate level, and that's how the levels db is. Okay, easy, straightforward. And with this, we have covered almost everything about LSM trees and the SST tables. Let me just recap it quickly, and we will done with this concept. So we went through the limitations of hash indexes. We went through these concepts such as file format, deletion of record, crash recovery, and everything about the hash indexes. And we came up with the new solution, which is sorted string tables. How we can use this new solution for the to resolve the limitations of the existing system, which is hash indexes. We understood how this compaction and merging works after sorting it, and how sorting will help us in retrieving the data in logarithmic scale. How we can use the self-balancing data structures to maintain the sorted structure of the hash indexes, and maintain the same structure in the disk as well. And we went over the recap, wherein we saw how writes work, how read works, and how merging and compaction work, and what are the different merging and compaction strategies and performance optimization that we can use. We also see how the performance degrades, and how to, if the key doesn't exist in the database, and how to solve it using the Bloom filters. So that is about it. Let me switch to this screen. I think that is about it. I hope you understood the overall concept about the LSM trees. And in the next video, in the part 3 of this video, we will go over the B trees and the more advanced concepts, and how we can resolve all of the limitations of the LSM trees in the next thing. And after that, B trees and R trees, we will be done with the database evolution part, and then we will start the new concept about the data engineering. I am again getting the goosebumps. I don't know if you can see it, but I am getting goosebumps because this is so much exciting stuff for me. I mean, I'm getting excited to see how databases works, how databases return the queries when you fire up select star from this table, and then it will return all of the things in blazingly fast, in like literally milliseconds of the time. And how it actually works, it gives me thrill, it gives me these goosebumps, it gives me chills, and I hope it gave you the chills as well, and I hope you have that moment. That's how it works. Amey, thank you so much, and I hope you understood it. Let me know in the comments section down below. Throughout this video, I've only told you guys only once to subscribe this channel, but it would help me a lot, because it takes a lot of efforts to even make these videos. I have to allocate time apart from my existing schedule to make these kinds of videos, and I love making these videos for you guys. And I hope you're liking it. I hope you have the same passion as me. I hope you are getting excited as well. And with that note, I will see you in the next one. हंसते रहिए, हंसाते रहिए और खुश रहिए. And I will see you in the next one. See ya.